Machine learning. How computers learn from data. In the first episode, we introduced you to the fascinating world of artificial intelligence, covering its basics, history, and the profound impact it's having on our world. Today, we're going to dive deeper into one of the most crucial components of AI, machine learning, which is all about how computers learn from data to make decisions and predictions. Machine learning is a driving force behind many of the AI technologies we interact with every day. From recommendation systems that suggest what movie to watch next, to virtual assistants that understand our voice commands. By the end of this episode, you'll have a solid understanding of what machine learning is, how it works, and why it's so important. What is machine learning? Let's start with a simple definition. Machine learning is a branch of artificial intelligence that focuses on teaching computers to learn from data without being explicitly programmed for every single task. Think of it as giving the computer the ability to learn and improve over time, much like how humans learn from experience. For example, imagine you want to teach a computer to recognize pictures of cats. Instead of programming it with a list of rules to identify a cat, you give it thousands of pictures labeled cat and not a cat. The computer analyzes these images, learning to recognize patterns, like the shape of the ears, the presence of whiskers, or the size of the eyes. Over time, it gets better at identifying cats, even in new images it has never seen before. How does machine learning work? At its core, machine learning is about finding patterns in data and using those patterns to make predictions. The process usually involves three main steps. Training. This is where the computer learns from data. You provide it with a data set that contains examples of the task you want it to learn, like identifying cats in images. The computer processes this data, looking for patterns and relationships. Validation. After the computer has been trained, you test it on new data to see how well it performs. This step helps you fine-tune the model and make adjustments if needed. Prediction. Once the model is trained and validated, it can be used to make predictions on new unseen data. For example, if you show it a new picture, it can predict whether there's a cat in the image. Types of machine learning. Machine learning can be divided into three main types, each with its own approach to learning from data. 1. Supervised learning. Supervised learning is like a teacher-student relationship. The computer is trained on a dataset where each example is labeled with the correct answer. It's like showing the computer a flashcard with a picture of a cat and the word cat written underneath. The computer learns to associate the features of the image with the label cat. Let's say you want to teach a computer to recognize different types of fruits. You would provide it with a dataset of images labeled apple, banana, orange, etc. The computer learns to recognize the color, shape, and texture of each fruit. After enough training, it can look at a new image and correctly identify the fruit. Supervised learning is widely used in applications like image recognition, speech recognition, and spam detection. For instance, your email's spam filter is trained using supervised learning to recognize patterns in emails that are likely to be spam. 2. Unsupervised learning. In unsupervised learning, the computer is given data without any labels and has to figure out the patterns on its own. It's like giving a child a box of mixed toys without telling them what they are. The child might group the toys by color, size, or shape, even though they don't know the names of the toys. Let's go back to the fruit example. If you gave the computer a bunch of images of fruits without any labels, it might group the images based on similarities, such as all round fruits in one group and all long fruits in another. The computer doesn't know the names of the fruits, but it can identify clusters or groups based on their features. Unsupervised learning is often used for clustering, which is grouping similar items together, and for finding hidden patterns in data. For example, retailers might use unsupervised learning to segment customers based on their purchasing behavior, helping them tailor marketing strategies for different customer groups. 3. Reinforcement learning. We discussed reinforcement learning in the previous episode, but let's briefly recap. Reinforcement learning is a type of machine learning where the computer learns by making decisions and receiving feedback in the form of rewards or penalties. It's like teaching a dog new tricks by giving it treats when it does something right. For example, a computer playing a video game might start by moving randomly. If it scores points, it receives a reward, and if it loses, it receives a penalty. Over time, it learns which actions lead to the best outcomes and improves its gameplay. Reinforcement learning is used in robotics, where robots learn to perform tasks by trial and error, and in game AI, where characters learn to adapt to the player's strategies. Key algorithms in machine learning. Now that we understand the types of machine learning, let's explore some of the key algorithms that power these methods. These algorithms are like recipes that the computer follows to learn from data. 1. Linear regression. Linear regression is one of the simplest and most commonly used algorithms in supervised learning. It's used for predicting a continuous outcome, like the price of a house based on its size. The idea is to find a straight line, or linear relationship, that best fits the data points. For example, if you have data on house prices and their corresponding sizes, linear regression helps you draw a line through the data points that can predict the price of a house based on its size. The better the line fits the data, the more accurate the predictions will be. 2. Logistic regression. Despite its name, logistic regression is actually used for classification tasks, where the goal is to predict a category rather than a continuous value. It's commonly used when you want to classify something into one of two categories, like whether an email is spam or not spam. Logistic regression works by estimating the probability that a given input belongs to a certain category. For example, based on the words in an email, the algorithm estimates the probability that the email is spam. If the probability is above a certain threshold, the email is classified as spam. 3. Decision trees. A decision tree is a flowchart-like structure, where each node represents a decision based on a feature of the data, and each branch represents the outcome of that decision. It's like playing 20 questions, where each question helps you narrow down the possibilities. For example, if you're trying to classify animals, the first decision might be, does it have feathers? If yes, it's likely a bird. If no, it could be a mammal. The tree continues to split the data based on features until it reaches a final decision. Decision trees are easy to understand and interpret, making them popular for applications like customer segmentation and credit scoring. 4. Random forests. A random forest is like a team of decision trees working together. It's an ensemble method, meaning it combines the predictions of multiple decision trees to improve accuracy. Each tree in the forest makes a prediction, and the random forest takes a vote on the most common prediction. For example, if you're using a random forest to classify flowers based on their features, each tree might make a slightly different prediction. By averaging the predictions, the random forest is more likely to get the correct answer than any individual tree. Random forests are powerful because they reduce the risk of overfitting, which is when a model performs well on training data, but poorly on new data. 5. Support vector machines, SVMs. Support vector machines are used for classification tasks, where the goal is to find the best boundary that separates different classes. Imagine drawing a line on a graph to separate points that belong to different categories. SVMs work by finding the line, or hyperplane, that maximizes the margin between the two classes. The larger the margin, the better the model is at generalizing to new data. SVMs are particularly useful when the data has clear boundaries and when the classes are well separated. 6. K-nearest neighbors, KNN. K-nearest neighbors is one of the simplest machine learning algorithms. It's based on the idea that similar things are near each other. When you want to classify a new data point, KNN looks at the K closest points in the dataset and assigns the most common label among them. For example, if you want to classify a new type of fruit, KNN might look at the nearest fruits in the dataset and choose the label that appears most often. If most of the nearest fruits are apples, the new fruit is likely an apple. KNN is easy to implement and works well for small datasets, but it can be slow and inefficient for large datasets. Applications of machine learning. Machine learning is not just a theoretical concept, it has practical applications across various industries. Let's explore some of the most impactful applications of machine learning. 1. Healthcare. Machine learning is revolutionizing healthcare by enabling early disease detection, personalized treatment plans, and predictive analytics. For example, algorithms can analyze medical images to identify tumors or predict patient outcomes based on historical data. Machine learning is also used to develop personalized medicine, where treatment plans are tailored to the individual patient based on their genetic makeup, lifestyle, and other factors. This approach has the potential to improve the effectiveness of treatments and reduce side effects. 2. Finance. In the financial sector, machine learning is used for fraud detection, algorithmic trading, credit scoring, and personalized financial services. The ability to process large volumes of data quickly and accurately makes machine learning indispensable in finance. For example, banks use machine learning algorithms to detect unusual patterns in transactions that might indicate fraud. These systems learn to recognize the typical behavior of an account and flag any deviations for further investigation. Algorithmic trading is another area where machine learning is making a big impact. Algorithms analyze market data in real time and make trading decisions at speeds that are impossible for humans, leading to more efficient and profitable trades. 3. Retail. Machine learning powers recommendation engines, which suggest products to customers based on their browsing and purchasing history. It also optimizes inventory management and pricing strategies. For example, when you shop online, machine learning algorithms analyze your previous purchases and browsing behavior to recommend products you might like. This personalized shopping experience can increase sales and customer satisfaction. Retailers also use machine learning to forecast demand, ensuring they have the right products in stock at the right time. By analyzing historical sales data, these algorithms can predict future trends and help retailers make better decisions about inventory management. 4. Transportation. Autonomous vehicles are one of the most talked about applications of machine learning. These vehicles use a combination of sensors, cameras, and machine learning algorithms to navigate roads and avoid obstacles. For example, self-driving cars use machine learning to recognize traffic signs, detect pedestrians, and make decisions about when to brake, accelerate, or turn. The algorithms learn from vast amounts of driving data to improve their performance and ensure the safety of passengers and pedestrians. Machine learning is also used in route optimization, helping logistics companies plan the most efficient routes for delivery trucks. By analyzing traffic patterns, weather conditions, and other factors, these algorithms can reduce fuel consumption and delivery times. 5. Natural language processing, NLP. Natural language processing, NLP, is a subfield of AI that focuses on the interaction between computers and human language. Applications include language translation, sentiment analysis, chatbots, and voice assistants. For example, NLP algorithms power translation services like Google Translate, enabling real-time communication between people who speak different languages. These algorithms learn from vast amounts of text data to improve the accuracy and fluency of translations. Sentiment analysis is another popular application of NLP, where algorithms analyze social media posts, reviews, and other text data to determine the sentiment behind the words. Businesses use sentiment analysis to understand customer opinions and improve their products and services. Challenges and ethical considerations in machine learning. While machine learning has enormous potential, it also comes with challenges and ethical considerations that need to be addressed. 1. Data quality and bias. Machine learning models are only as good as the data they're trained on. If the data contains errors, biases, or is not representative of the real world, the model's predictions will be flawed. For example, a facial recognition system trained on a dataset that lacks diversity may not perform well on people with different skin tones. Addressing data quality and bias is crucial for ensuring that machine learning models are fair and reliable. This involves careful data collection, cleaning, and monitoring to identify and mitigate biases. 2. Interpretability and transparency. Many machine learning models, especially deep learning models, are often referred to as black boxes because their decision-making process is not easily interpretable. This lack of transparency can be problematic in critical applications like healthcare and finance, where understanding the rationale behind a decision is important. Researchers are working on developing more interpretable models and techniques for explaining the decisions made by complex algorithms. This is an important step towards building trust in machine learning systems and ensuring that they are used responsibly. 3. Privacy and security. Machine learning models often rely on large amounts of personal data to make accurate predictions. This raises concerns about privacy and data security, especially when sensitive information is involved. Ensuring that data is collected, stored, and used in a secure and ethical manner is essential for protecting individuals' privacy. This includes implementing strong encryption, anonymization techniques, and adhering to data protection regulations. The future of machine learning. The future of machine learning is full of exciting possibilities. As the field continues to evolve, we can expect to see even more powerful and versatile applications. 1. Explainable AI. One of the key areas of focus for the future is explainable AI, where the decision-making process of algorithms is transparent and understandable to humans. This is crucial for building trust in AI systems and ensuring that they are used ethically. 2. Integration with other technologies. Machine learning is increasingly being integrated with other technologies, such as the Internet of Things, IoT, and blockchain. This integration enables the development of intelligent systems that are more secure, adaptive, and capable of handling complex tasks. 3. Quantum computing. Quantum computing holds the potential to revolutionize machine learning by providing unprecedented computational power. This could enable the training of more complex models on a scale previously unimaginable, leading to breakthroughs in fields ranging from materials science to AI. 4. Machine learning for social good. There is growing interest in using machine learning for social good. such as addressing climate change, improving healthcare, and reducing poverty. By leveraging the power of machine learning, we can develop innovative solutions to some of the world's most pressing challenges. Conclusion. In this episode, we've explored the world of machine learning, from its basic concepts to its real-world applications and future potential. We've seen how computers learn from data, and how this powerful technology is shaping the future of industries ranging from healthcare to finance. In the next episode, we'll dive deeper into deep learning, a subset of machine learning that has achieved remarkable success in recent years. We'll explore how neural networks are trained and how they power some of the most impressive AI systems today. Thank you for joining us on this journey through machine learning. Don't forget to subscribe and hit the notification bell to stay updated with our AI series. See you in the next episode.